Imagine, just for a moment, that you are the lead architect of this highly secure, state-of-the-art bank vault.
Okay, I'm picturing it.
Right. And the entire architecture relies on one absolutely immutable rule. The physical vault key must remain locked inside the manager's secure office.
Makes sense. Keep the key in the most secure zone.
Exactly. So the entire building's security apparatus, the biometric scanners, the laser grids, the motion detectors, they are all calibrated around that single geographic assumption.
Right, because if the key moves outside that office, the system immediately assumes a breach has occurred.
Yes. But then an executive mandate comes down from corporate. To streamline operations across, multiple branches, all vault keys are now being relocated to a centralized public lobby kiosk.
Oh, wow. That is a terrible idea.
It really is. The vault itself hasn't weakened, right? But the geographical logic that the security system depends on is just entirely inverted.
Which instantly puts the architecture into this state of conflict. I mean, the security protocols are hard-coded to trust a very specific perimeter.
Exactly.
So when you shift that credential to a zone designated for general traffic, the system doesn't just dynamically adapt. It fails closed.
It triggers an absolute lockdown.
Yeah, because it just cannot reconcile that new location with its internal security matrix.
And that structural conflict is the exact environment we are stepping into today. So welcome to another deep dive.
You got to be here.
Our mission today for you is a granular architectural breakdown of a scenario designed to really test the limits of your Linux administration skills.
We're looking at a high difficulty challenge, right?
We are. This is from the Red Hat Certified System Administrator, or the RHCSA exam. Specifically, we're aiming at RHEL 10 environments today.
Nice.
Our source material is a lab scenario summary titled RHCSA 040 Season 2 Scenario 15 Centralized SSH Key Linkage. And we sourced this from Djere.com.
It is such a critical scenario to master, honestly,
Oh, yeah,
because the RHCSA isn't about, memorizing trivia. It's a performance-based exam.
Right, you're actually doing the work.
Exactly. You inherit a broken system or a complex deployment requirement, and you have to manipulate the live operating system to comply.
And I see scenarios like this constantly in enterprise environments. The premise here is we have an automated deployment application, right? And it needs to authenticate to our RHEL 10 server as a local user named deploy manager.
And naturally, it requires SSH keys rather than passwords for that automation. You can't have a human typing a password at 2 a.m.
Exactly. But here's the architectural twist. Here's our key in the lobby problem.
Okay, let's unpack this.
Due to a system migration, all public keys for deployment services have to be centralized. They can no longer live in the standard home directory, the usual /home/deploy manager /dot/ directory.
Right, the default location.
Right. Instead, they are forced into a custom centralized location, specifically /var/deployment/keys.
Okay, so we are tasked with building a symbolic link from the user's home directory to this non-standard /var directory.
Yes, and we have to somehow force the system to actually accept it.
Which is easier said than done. But, centralizing SSH keys like this is incredibly common when you start scaling up infrastructure.
Oh, absolutely.
When you integrate massive configuration management systems, like Ansible, or you're orchestrating hundreds of nodes, scattering credentials across individual user home directories just becomes this massive auditing nightmare.
It's impossible to track who has access to what.
Right. So administrators often prefer to consolidate those keys into a centralized mount point, maybe backed by an NFS share or a dedicated secure logical volume. It just streamlines rotation and access control.
But the moment you move cryptographic keys outside of the standard home directory, you trigger defensive mechanisms deep within the Linux kernel.
You really do.
So I want to break down those defensive mechanisms for you because our source explicitly rates this as a high difficulty lab.
And it deserves that rating.
It seems like the difficulty doesn't stem from the complexity of, a single command. It's more about navigating the collision of two completely independent security subsystems.
What's fascinating here is that you're fighting a two-front war.
Right. I'm assuming the first major roadblock is the OpenSSH daemon itself, specifically how SHD handles directory traversal.
Exactly. The OpenSSH daemon operates with an extremely high level of paranoia.
As it should.
Right. And it's governed primarily by the strict modes directive, which is enabled by default.
Okay, so what does strict modes actually do?
Well, when the user attempts to authenticate, SHD doesn't just blindly read the authorized keys file. It utilizes the stat system call to inspect the ownership and permissions of the key file itself, the dots directory, the user's home directory, and potentially even higher up the directory tree.
Wow, it checks the whole path.
It demands that the entire path be owned by either the authenticating user or by root. And it absolutely forbids write permissions for group or other users.
So it's like trying to get a VIP into a highly secure building. OpenSSH is the ID checker at every single door down the hallway.
That's a great analogy.
It's actively hunting for any vector where a lesser privileged user might have, swapped out the key or redirected the path.
Right. If I'm swished, I need absolute mathematical certainty that the file I am reading hasn't been tampered with by some rogue process running alongside it.
So if even a single directory in that traversal path allows, let's say, group write access, SSH interprets that as a compromised chain of trust.
Yeah, and it drops the connection immediately to protect the server. It won't even try to authenticate you.
Okay, so that covers the daemon's internal logic. But the second, and arguably much heavier force we are fighting here is the kernel itself.
Ah, yes, SELinux.
Exactly, because we are taking a file containing a sensitive cryptographic key, and we are placing it in /var, which is a directory hierarchy generally reserved for variable data, system logging, and spool files.
And this is where we transition from discretionary access control.
Which is the standard read, write, execute permission.
Exactly, to mandatory access control. SELinux, which was originally developed by the NSA, operates by assigning a security context, or label, to every single file, process, and port on the system.
And those labels are stored in the file system's extended attributes, right?
Correct. The SELinux policy engine acts as this massive matrix. So when the RHEL process, which is running in its own confined domain, attempts to read a file, the kernel intercepts the system call.
It literally pauses the read operation.
Yes. It checks the matrix and asks, is the SSH daemon allowed to read a file labeled as variable data?
And going back to our analogy, SELinux is the background check, validating if the room itself is even allowed to hold VIPs in the first place.
Exactly. And the default policy matrix obviously dictates that a network-facing authentication daemon has absolutely no business reading random spool files or generic variable data.
So it explicitly denies the action.
Totally. Even if the standard file permissions are wide open, I mean, even if you could mod the file to 777, the kernel will block the system call at the mandatory access control layer.
The file system won't even pass the data to the daemon.
Not a single byte.
Okay, this sets the stage perfectly for you. We have to appease Sashid's strict ownership checks, and we have to rewrite the SELinux policy matrix to allow the read operation.
It's a lot of plates to keep spinning.
Let's look at the implementation steps provided in the source. The very first action we take as the root user is preparing our environment.
Step 1.
We run a conditional check. Quote, if not rpm-q policycrutils python utils, then dnf install -y policycrutils python utils phi.
Okay. Checking for a specific package.
Yeah, I know RHEL 10 leans really heavily into minimalism. They drop a lot of legacy tooling from the base install to reduce the attack surface.
Which is smart.
Right, so I'm guessing this package isn't included in a minimal install, but is strictly required for modifying the SELinux policy store later on.
It is essential. While basic SELinux commands, like systatus or checkon, might be present on a minimal install, manipulating the persistent policy database requires this managed utility.
And Symbolic is largely written in Python.
Yes. Hence the Python utils package dependency. Without it, you just cannot permanently add new file context mapping rules.
So if a candidate tries to take a shortcut here.
If you attempt the exam and try to manually relabel the files using only checkon, you will fail the objective.
Oh, wow. Why?
Because just checkon only modifies the extended attributes temporarily.
Right.
The moment the system reboots, or someone runs the restore con, your changes are wiped out by the default policy database.
A vital distinction for anyone taking the exam, persistence is graded, not just the temporary state.
You have to make it survive a reboot.
Okay, moving on. We create our deployment user. The command is useradm-s/bin/bash deploy manager.
Pretty standard user creation.
Well, I typically omit the -m flag to avoid creating a home directory for service accounts, especially since we are intentionally moving the SSH keys out of the home directory anyway.
That's a fair point.
But I'm assuming that even with a symbolic link, SHEG's internal pluggable authentication module, the PAM stack, requires a valid home directory to execute a check you're into upon successful login.
That is a highly accurate assessment of the session initialization sequence.
So if the directory doesn't exist, the session setup might just crash before it even launches the shell?
Exactly. When Shift authenticates a user, it hands off the session setup to PAM. And PAM handles environment variables, resource limits, and crucially, setting the working directory to the path specified in /etc/password.
Right.
If /home/deploy manager does not exist, the choose your system call fails. Depending on the exact PAM configuration, this can immediately terminate the session.
Rendering all your carefully crafted key authentication completely useless.
Precisely. Furthermore, because we must use a symbolic link later to trick sudo into finding the key, that link must physically reside in the expected .swoosh location.
Right, it needs a place to live. And the -as/bin/bash ensures that once PAM sets up the session, it actually spawns a functional born-again shell.
Right, because if an automated CI/CD pipeline is connecting, it needs a real command interpreter to execute its payload scripts.
It can't just be handed /spin/monitor again.
Exactly. Service accounts used purely for, say, tunneling or port forwarding might use knowledge in, but an automated deployment manager actively executing remote code. It requires a standard shell environment.
Makes total sense. Okay, once the user is structured in the system, we build the non-standard file structure that is really the crux of this scenario.
There we go.
We execute mondadir-p/var/deployment/keys. Then we move aggressively into locking down the permissions.
This is where candidates usually mess up.
The source specifies chown-r deploy manager :deploy manager/var/deployment, followed by trimod 700 on both the deployment and keys directories.
Those permissions have to be exact.
Let's dissect the mechanism here. We aren't just setting these permissions as, like, a best practice. We are doing this specifically to preempt those strict modes checks we talked about.
Yes, we are actively satisfying the daemon before we even generate a key.
When we set chmod 700, we are granting read, write, and execute bits exclusively to the owner. The read and write bits are obvious, but the execute bit on a directory is what actually permits path traversal via the stat system call, correct?
It is the traversal bit. In the Linux file system architecture, if a directory lacks the execute bit for a specific user, that user cannot access the metadata of the files contained within it.
Even if they know the exact file name?
Even then,
Yeah.
they cannot CD into it, and more importantly for our scenario, an external process cannot traverse through it to reach a child file.
So by setting both the parent/var/deployment and the child keys directory to 700,
And ensuring deploy manager owns them.
we guarantee that when the SSH daemon drops its privileges to perform its security checks as the user, it can cleanly traverse the path without encountering any group-writable vulnerabilities.
Exactly. If we had left the permissions at the default 755, where group and others can read and execute,
Shmost would instantly flag the custom path as insecure and drop the authentication attempt silently.
it would view a world-readable directory path to an authentication key as an unacceptable risk. The integrity of the authentication chain relies on the absolute isolation of those files.
Okay, so that sets up our environment. Now we move to section 2, the core implementation, where we actually deal with the cryptography and the symbolic link itself.
Here's where it gets really interesting.
We execute this as the root user. Sesh keygen -trsa-b 4096-f/root/dot/deploydist key -n and then 2 empty quotes.
It's a very specific key generation command.
I want to push back on the parameters here a little bit. We're using RSA at 4096 bits.
Right.
While mathematically robust, RSA is computationally heavier and just older than elliptic curve cryptography, like ED 25519.
That's true.
And ED 25519 is often recommended as the modern standard for SSH. So I'm assuming the source relies on RSA here because it remains universally compatible across older legacy enterprise systems, like stuff that might be integrated into this hypothetical deployment pipeline.
The prevalence of RSA in enterprise environments is deeply entrenched. You're right that ED 25519 offers better performance and smaller key sizes for comparable security.
Much smaller.
Right. But many older hardware security modules, legacy configuration management databases, and specific enterprise compliance frameworks still mandate RSA.
It's just everywhere.
And at 4096 bits, the computational cost of factoring the primes is considered secure against classical computing brute force attacks well into the foreseeable future.
So for an exam scenario simulating a massive, perhaps slightly aging enterprise architecture, RSA remains a highly pragmatic choice.
Exactly. It's realistic.
But I'd argue the most critical flag in that command isn't the algorithm, it's the -n with the empty quotes.
Yes, the empty passphrase.
We are generating an unencrypted private key directly on the disk, no passphrase. If this were a human user's laptop, security teams would have an absolute meltdown.
Oh, they would revoke your access immediately.
Right. A stolen laptop would mean instantaneous, unauthenticated access to the server infrastructure.
In a human context, it is a catastrophic vulnerability. But in the context of machine-to-machine automation, it is a structural necessity.
Because there's no human to type it in.
Exactly. If a Jenkins pipeline or an Ansible control node triggers a deployment across a fleet of servers at 2:20 near AM, there is no interactive TTY session available to prompt a human for a passphrase.
I mean, you could theoretically use an ASH agent to hold the decrypted key in memory, right?
You could, but managing agent forwarding and socket permissions for background daemon processes is incredibly complex.
And brittle.
Very brittle. It introduces unacceptable friction into automated scaling. So, the accepted enterprise risk model relies instead on strict file system permissions on the control node to protect the unencrypted private key.
So the security perimeter shifts from cryptographic encryption of the key file to the physical and logical access control of the server holding the key.
Precisely. You lock down the server holding the key rather than locking the key itself.
Okay, so we have our key pair. The next step is placing the public key into our centralized location.
Flipping the script on the default locations.
Right. The command is cat/root/dot/deploy_key.pub, and we redirect that into /var/deployment/keys/authorized keys.
We pipe the contents directly into a new file in the /var structure.
Then we do this crucial ownership and permission lockdown on the file itself. Chown deploy manager, :deploy manager on that authorized keys file.
Followed immediately by SCOD 600.
Right. We drop the execute bit entirely here because it's purely a data file read by the daemon.
Giving an authorized keys file executable permissions is illogical from a system design standpoint.
It would probably trigger auditing tools too.
Immediate suspicion. It is a static text file containing cryptographic public keys. It should never be executed as a binary or a script.
Okay, so at this point, the key exists securely locked in /var, but the SSH daemon is completely blind to it.
It has no idea it's there.
Because squad is hard-coded to look in the user's home directory. We have to build the bridge.
The symbolic link.
First, we create the facade that stop expects. mcodir-p/home/deploy manager/.sush, and we secure it with chirmud 700.
Keeping those strict permissions intact.
Then we execute the symbolic link, which aligns with Objective 1.9 on the RHCSA. The command is ln-a/var/deployment/keys/authorized keys /home/deploy manager/.sush/authorized keys.
A very long command, but a very important one.
Let's dive into the VFS, the virtual file system layer here. I know a hard link directly points a new file name to the exact same underlying inode on the disk.
Right.
Why use a symbolic or soft link instead of a hard link? Wouldn't a hard link bypass some of the complexity we're about to face?
That is an excellent architectural question. Hard link would indeed bypass some complexity because it is entirely indistinguishable from the original file.
It's just a second directory entry pointing to the same data blocks.
Exactly. However, hard links have a fatal limitation. They cannot span across different file systems or mount points.
And in an enterprise server, /home and /var are almost certainly mounted on completely different logical volumes.
Almost always. /var frequently resides on a heavily monitored, often separately provisioned logical volume to prevent log files from filling up the root partition.
Oh, right, because if /var fills up and it's en route, the whole system crashes.
Exactly. So if you attempt to hard link a file in /home to an inode in /var, the kernel will reject the operation with a cross-device link error.
So a hard link is just geographically impossible here.
Right. A symbolic link, conversely, creates a brand new inode. It is an entirely separate file, but its data payload is simply a text string containing the absolute path to the target file.
So when the kernel's file system driver encounters a symbolic link during a read operation, it pauses.
It reads the string inside the link and dynamically redirects the system call to the new path. It allows for transparent redirection across physical disks and network mounts.
Which is brilliant, but it introduces a massive trap for exam candidates.
Oh, this is the trap.
We have the link in place. The target file in /var is owned by deploy manager, but the root user executed the ln-s command.
Meaning the link itself is owned by root.
Right, and the source specifies the next command as chown-h deploy manager :deploy manager /home /deploy manager // authorized keys.
Notice that -h flag.
Wait, why the -h flag? Doesn't chown usually just follow the link? I mean, if a candidate forgets the -h flag and just runs chown, the kernel uses the standard chown system call.
Yes.
And standard chown automatically dereferences the link, right? It follows the string, goes to /var, and reapplies the ownership to the target file.
It ignores the link entirely and modifies the destination. The problem is that the link file itself, residing in the user's .whoosh directory, remains owned by root.
Oh. And when Strahd performs its strict modes checks,
It traverses into the .shesh directory, inspects the authorized keys file, and sees a file owned by root.
even though it's just a pointer.
Even though it's just a pointer, Strahd evaluates the ownership of the pointer itself.
Yeah.
Finding a root-owned file in the user's security path is a violation of its trust model, and authentication is immediately denied.
That is wild. So by adding the -a flag, we force the command line utility to utilize the lchown system call instead.
Correct.
And lchown explicitly operates on the symbolic link itself without dereferencing it.
It alters the ownership of the pointer, satisfying Shrid's requirement that the user owns every component in the chain.
It is a profound demonstration of understanding the nuances of system calls and default utility behaviors. I mean, missing that single flag leaves a silent, fatal flaw in the architecture.
A lot of candidates fail the lab right there, and they have no idea why.
Because of the silent failure. Let's talk about that.
Yeah.
We've built the structure, applied perfect permissions, and bridged the gap with a flawlessly owned symbolic link.
The discretionary access control is perfect.
But if we stopped here and tried to authenticate, it would fail. And as the source notes with a massive pro tip, OpenSSH will silently reject authentication.
It doesn't broadcast why it fails.
So let's discuss how an administrator actually traces this in the real world. The client just sees, permission denied, public key.
Which is the most generic error ever.
Right. If I'm troubleshooting this, I'm not staring at the client. I'm going to the server logs. I'd immediately pull up journal-dash-zushes or check/var/log/secure. What am I actually looking for in those logs?
Well, the logs are often frustratingly opaque unless you increase the log level in the shtinfig.
Ah, of course.
Standard logging might just show connection closed by authenticating user. It's not helpful. However, if you elevate the logging to verbose or debug, the daemon will expose its internal state machine.
And then you'd see the actual error.
You will see explicit messages stating authentication refused, bad ownership or modes for directory /var/deployment/keys.
That's the golden ticket for debugging. And if you can't alter the daemon's config, I suppose you could attach strace to the shtud process and watch the system calls in real time.
You could?
Watching exactly which stat call returns a failure or which open call gets rejected by the kernel.
Strace is the ultimate source of truth, though parsing the output requires really deep understanding of kernel interactions.
Definitely not for the faint of heart.
No. But in this specific scenario, even if Scrished is perfectly satisfied with the permissions, and Strace would reveal an open system call returning an ECCES error, permission denied.
Wait, really? Even with perfect permissions?
Yes. Not from the file system, but from SELinux.
Which brings us to Section 3, the silent rejection and tackling the SELinux beast, Objective 10.5, SELinux contexts.
We connect this to the bigger picture. This is where the mandatory access control flexes its muscles.
We established earlier that our custom directory inherently inherited the vart label.
Right, because it was created in /var.
And the SSH daemon operates in the shishd domain. The kernel checks its matrix and finds absolutely no rule allowing shish to read vart.
So the operation is killed in memory.
To resolve this, we have to basically rewrite the policy blueprint. The source command is symanage fcontext --t shamet, followed by a string, in quotes, /var/deployment open parenthesis /.* close parenthesis ?
That's a mouthful.
Let's unpack the mechanism here. We are using symanage fcontext to add, that's the dash, a new type rule, which is the -t shamet.
We are declaring that this custom path should be treated securely, just like a standard SSH home directory.
And the kernel already has rules allowing Shari to read shamet.
Exactly. We are just applying a known safe label to a new location.
But the path definition string, that /var/deployment part with the parentheses, is what fascinates me. This isn't a simple file path. It's a Perl-compatible regular expression, or PCRE.
It is.
How does the SELinux policy engine process this regex?
The SELinux file context database, which is typically located in /etc//SELinux/targeted/context/files, utilizes regular expressions to map labels to dynamically changing file systems.
Because files come and go constantly.
Right. When we define that string, the engine breaks it down logically. The base string /var/deployment anchors the expression.
Okay, so that's the starting point.
Then the parentheses create a capture group. The dot matches any single character, and the asterisk acts as a multiplier, meaning 0 or more of any character.
So dot asterisk means literally anything inside that directory.
Yes. And crucially, the question mark at the very end makes the entire preceding group optional.
Meaning it applies to the deployment directory itself and optionally anything inside of it.
Precisely. So mechanically, if the system creates a new file called /var/deployment/keys/nuki.pub,
the regex engine parses it, matches the root directory, matches the trailing slash, and matches the file name, instantly mapping it to the showmat policy rule.
Exactly. It ensures that the labeling survives infrastructure changes.
So you don't have to do it manually every time.
Right. If a configuration management tool deletes the directory and recreates it, or drops 50 new keys into the folder, the administrator doesn't have to manually relabel them. The policy blueprint explicitly dictates their context based on their path matching that regular expression.
But Symanage only updates the blueprint, right? It writes the regex to the file context.local file. It does absolutely nothing to the live extended attributes on the disk.
Nothing at all.
If we tried to log in right now, we would still fail.
You'd still get blocked.
We have to force the kernel to read the blueprint and apply it. So we run restorecon-rv/var/deployment.
The magic command.
I'm assuming restorecon initiates a recursive, that's the -r, walk down the directory tree.
It does.
And for every file it encounters, it compares the current path against the compiled PCRE database. When it finds a match, it utilizes the subsystem call to overwrite the SELinux security context in the inode's extended attributes.
That is the precise sequence of operations. And the -v flag makes the utility verbose, outputting to the standard out the explicit changes it makes.
So we can see the magic happen.
You will physically see the label transition from vart to showmat on your terminal. And at the exact moment that subsystem call completes, the SELinux block is lifted.
The kernel's policy matrix is satisfied.
And the mandatory access control layer will finally permit the SSH daemon's read request.
The architecture is finally aligned. Both security forces the daemon's discretionary access control checks, and the kernel's mandatory access control rules are satisfied.
It's a beautiful thing when it all comes together.
Which leads us to Section 4, the proof of work and the comprehensive cleanup.
So what does this all mean? How do we prove we did it right?
Right, because in an exam or a production rollout, assuming it works is a guaranteed path to failure. We must prove the cryptographic authentication functions, prove the symbolic link resolves, and prove SELinux permits the transaction.
We need empirical evidence.
The source provides a really comprehensive single-line testing command. /-i/root/dosh/deployduskey- circthost key checking equals no deploy manager at localhost, followed by a quoted command. Wami /l/home/deploy manager /dot/authorized keys.
This is a brilliant piece of automation testing.
We are invoking SSH, passing the specific identity file, that's the -i containing our unencrypted private key.
Right.
We are connecting as the deploy manager to localhost, but the inclusion of -o stricthost key checking equals no is what makes this production ready.
I love that they included this detail.
Why? I mean, when an SSH client connects to a server for the very first time, it receives the server's public host key to establish that secure encrypted tunnel, right?
Typically utilizing a Diffie-Hellman key exchange.
And the client checks this key against its known host file. If it's not there, it stops the entire process and interactively prompts the user on the TTY to manually verify the cryptographic fingerprint.
Which is catastrophic for a headless automated script.
Right, because there's no user to hit yes.
Exactly. A CI/CD pipeline running Jenkins cannot interpret an interactive prompt. It will simply hang indefinitely, waiting for standard input that will never arrive, eventually causing the pipeline to time out and fail.
Okay, but I would normally argue that bypassing host key checking opens the connection up to a man-in-the-middle attack.
It absolutely does.
If a rogue server hijacks the IP routing, the automated script would blindly hand over its credentials.
In an untrusted public network, bypassing host verification is a critical security flaw. However, in the context of controlled internal CI/CD environments,
Where DNS, ARP tables, and IP routing are tightly governed by software-defined networking.
right, in that specific environment, the risk of an internal MITM is heavily mitigated. The necessity of automated scaling just outweighs the localized risk, especially since we're using cryptographic keys rather than transmitting a reusable password.
So the -o strict host key checking equals no parameter just instructs the SSH client to automatically accept the host key, bypassing the TTY prompt entirely.
It forces the connection through seamlessly for testing.
We append the remote execution payload, in quotes, WAMI, and then the ELS command. The SSH client negotiates the tunnel, authenticates using our custom-linked key structure, executes the payload, and returns the standard output,
And the expected output of WAMI is deploy manager.
definitively proving the authentication succeeded.
And the output of the ls-l command reveals the symbolic link arrow pointing to /var/deployment/keys/authorized keys.
Proving the client connected through our customized VFS bridge.
It is empirical proof that the architecture holds.
But the source includes one final, highly specific validation step regarding SELinux, els-zd/var/deployment/keys.
While the successful SSH login implicitly proves SELinux allow the read operation, an administrator must explicitly verify the context labels.
Especially before deploying this configuration across a fleet of servers.
Exactly. The -z flag retrieves the SELinux security context from the extended attributes.
And the expected output string is pretty dense. It reads, unconfined do :objectors :shemet :0.
For a junior admin, this just looks like arbitrary hex code.
Let's decode the architecture of this string, because understanding it is vital for the RHCSA. It's a colon-separated mapping of user, role, type, and sensitivity level.
Let's break it down.
The first field, unconfined do, is the SELinux user identity. Since we haven't implemented strict user-based mandatory access control, it just defaults to unconfined.
The second field, objector, represents the SELinux role. In this context, objector explicitly designates that this entity is a passive file or directory resting on the storage medium.
As opposed to an active running process that would have a different role assignment.
Right.
The third field is the critical component, the type enforcement label. This is what the entire policy matrix revolves around. It must read shemet.
If it still reads vert, our restorecon command failed and the system is broken.
Type enforcement is the bedrock of targeted SELinux policies. The daemon's domain, shanedt, is evaluated strictly against the file's type, shemet.
Exactly. And the final field, 0, denotes the sensitivity and category levels.
Which are utilized primarily in multi-level security or multi-category security environments, right?
Yes. While crucial in highly classified military or intelligence deployments, where data must be segregated by clearance levels for a standard enterprise RHEL deployment and the RHCSA exam, a default 0 sensitivity is expected and completely sufficient.
The core verification rests entirely on that shemet type field.
That's the one you need to watch.
Okay, the verification is absolute. We successfully decoupled the strict geographic requirements of OpenSSH from the restrictive zoning laws of SELinux, and we bent the operating system to support a non-standard enterprise architecture.
We did it.
However, the source mandates a final phase, the zero-trace cleanup. We must tear down everything we just built.
A good admin leaves no trace.
In my experience, administrators who skip the teardown phase during lab practice end up really sabotaging their own learning.
Oh, without a doubt.
If you leave lingering configurations, custom SELinux rules, or modified permissions on a practice server, you induce state drift. The next time you run a lab, it might succeed, not because you configured it correctly today, but because a residual rule from last week allowed it.
Which is a false positive.
Right. Infrastructure as code demands pristine, reproducible states, and your muscle memory must reflect that discipline.
Beyond study habits, the real-world implications of state drift are severe. I mean, leaving test keys, custom SELinux policies, or permissive directory structures on a server after a troubleshooting session effectively creates undocumented backdoors.
An attacker's dream.
An attacker scanning the internal network for vulnerabilities will exploit an orphaned, unencrypted 496-bit RSA key sitting in a /var directory long before they attempt to brute force a primary firewall.
Comprehensive teardown is a fundamental security practice. So let's execute the teardown logically, reversing our build process.
Step-by-step teardown.
First, we terminate any lingering processes associated with our test account. pkill-u deploy manager pipe true.
Okay. pkill.
Mechanically, pkill-u sends a sigterm signal to every process owned by that user ID. If the process doesn't terminate cleanly, it might require a sigkill, but pkill attempts a graceful shutdown first.
That's standard.
But the bash logic here, the pipe true, is particularly important for scripting. Why include that?
It utilizes bash's short-circuit evaluation. If pkill searches the process table and finds 0 active processes owned by deploy manager, the command returns a non-zero exit status.
Indicating a failure.
Right. If this command were part of an automated teardown script running with set-e, which forces a script to exit on any error, the entire cleanup process would halt immediately just because the user wasn't logged in.
Oh, so by appending pipe true, we...
If pkill fails, the true command executes and returns a success code, ensuring the bash script continues execution seamlessly.
It's just defensive scripting. We assume the user might not be logged in, and we handle the error gracefully. Once the processes are clear, we execute userdel-r deploy manager. The kernel removes the user from /etc/passroot and /etc/shadow.
But the -r flag is doing heavy lifting here.
It instructs userdel to consult /etc/login.defs and systematically delete the user's home directory and mail spool, completely wiping the standard .sester directory and our symbolic link from the file system.
If we omitted the -r, we'd leave an orphan directory owned by a user ID that no longer exists,
creating a confusing and potentially exploitable artifact.
Orphan files complicate auditing and can lead to permission clashes if that specific numerical UID is subsequently reassigned to a different user account in the future. Total eradication of the environment is required.
Next, we dismantle our custom infrastructure. A simple arm-arf/var/deployment recursively forces the deletion of our custom directory and the authorized keys file holding our public key,
Wiping the external structure.
We follow that by removing the unencrypted private key from root's home directory, rm-f/root/.sechesh/deploydiskey*. The asterisk acts as a wildcard, ensuring both the private key and the .pub public key variant are obliterated,
Leaving no trace of the keys.
But the final step is perhaps the most critical to preventing long-term state drift. Submanage fcontext-d-t showmet, and then our regex string again.
We are utilizing the exact same PCRE regex string, but substituting the -a flag for a -d flag,
which actively deletes the rule from the policy database. If an administrator simply deleted the /var/deployment directory, but left the SELinux rule in the database, what is the residual risk?
The risk lies in future system provisioning. The SELinux policy engine is persistent and decoupled from the immediate file system state.
So it remembers the rule forever.
Yes. If, a year later, a different administrator creates a directory called /var/deployment for an entirely unrelated, perhaps highly sensitive application,
the moment restorecon is run on the system, the kernel will apply the showmet label to that new data.
Exactly. Suddenly, the SSH daemon possesses the authorization to read files it has no business accessing, fundamentally compromising the mandatory access control architecture. You must excise the rule from the policy database.
It reinforces the concept that system administration isn't just about managing files. It's about managing the underlying logical matrices that govern the system's behavior long after the files are gone.
That is the essence of being a systems architect.
We have traversed a massive amount of architectural territory today. We analyzed the paranoid strict modes traversal checks of the OpenSSH daemon. We navigated the virtual file system layer to deploy symbolic links across disparate logical volumes.
We generated unencrypted cryptographic keys tailored for CI/CD automation.
And we successfully rewrote the SELinux mandatory access control policy utilizing Perl-compatible regular expressions to seamlessly map security context to non-standard directories.
It is a rigorous high-level exercise in manipulating the foundational security layers of RHEL 10.
The complexity of this scenario perfectly illustrates why Linux remains the dominant architecture in enterprise infrastructure. The security systems are immensely powerful and inflexible by default, designed to protect the system at all costs. but they provide the precise administrative tooling required to reshape their logic when the architecture demands it.
This raises an important question, though, a final thought to mull over.
Oh,
We saw today how OpenSSH will silently reject authentication for a minor permission slip-up anywhere in the directory path.
just totally silent.
It forces us to ask, in an era of automated lightning-fast deployment pipelines, how many other critical security systems in our infrastructure fail silently by design, leaving us to assume it's a network error rather than a permission safety net doing exactly what it was built to do?
A vital perspective for anyone architecting systems at scale. The silence of the kernel is usually the strongest indicator of its efficacy.
It's doing its job. You just have to know how to listen.
Thank you for joining us on this incredibly deep dive into system architecture. For those of you preparing for the RHCSA, or simply looking to elevate your understanding of Linux security integration, this scenario demands hands-on execution.
Have to practice it.
Spin up a virtual environment, trace the system calls, parse the SELinux logs, and deliberately break the configurations to observe how the kernel reacts. Mastering the interplay between these subsystems is what separates a user from an architect. Keep pushing the boundaries of your environments, and until next time, keep exploring.